In this screencast, we'll be examining adrenal corticotropic hormone and the adrenal cortex. The learning objectives of this screencast are as follows. We're going to continue to examine and discuss the tropic hormones released by the anterior pituitary gland. Our next one is adrenal corticotropic hormone, or ACTH. It targets the adrenal cortex and then causes the release of the adrenal androgens, aldosterone, and cortisol. So those are the additional hormones that we'll be discussing as well. And before we move on, I just want to remind you that for every hormone that we cover, you need to know all of these key features listed here. Adrenal corticotropic hormone is a tropic hormone released by the anterior pituitary gland, and it targets the adrenal cortex. Its name is very, very descriptive. Tropic, meaning it targets other endocrine organs, and adrenal corta tells you it targets the adrenal cortex. At this point, you're no stranger to the adrenal glands. They are found on top of the kidneys. In fact, it's often said that the kidneys wear the adrenal glands like hats. Renal refers to kidney, so you can think of the adrenal gland as adding to the kidney. And similar to the pituitary gland, the adrenal is really two different organs in one, sometimes referred to as two different glands. You have the adrenal cortex. Cortex means bark, so it's the outer portion. That's the one that we're going to be looking at now. And then you have the inner portion, which is the adrenal medulla. If you remember, the adrenal medulla is innervated by the sympathetic nervous system. Nervous stimulation from the sympathetic nervous system causes the adrenal medulla to release the hormones epinephrine, norepinephrine, and a little bit of dopamine. We are focusing on the glandular portion of the adrenal, which is the adrenal cortex. That is what is targeted and stimulated by the adrenal corticotropic hormone. So the hypothalamus releases corticotropin releasing hormone. That hormone targets the anterior pituitary gland, causing the release of adrenal corticotropic hormone. Adrenal corticotropic hormone then targets the adrenal cortex, causing the release of three separate hormones: the sex steroids, or adrenal androgens, aldosterone, and cortisol. Let's discuss the adrenal androgens first. Androgens are male sex hormones, and yes, believe it or not, the adrenal cortex of both males and females produce weak male sex hormones, or gonadocorticoids. Again, they're weak compared to testosterone. These adrenal androgens include androstenedione and dehydroepiandrosterone. And don't worry about knowing those two chemicals for the exam or a quiz. Both, when released into the bloodstream, when they interact with their target cells, they're converted to either the more potent androgen testosterone, or in some cases, they are converted to estrogen. There's a lot that we don't know about the role that these adrenal androgens play in the human body. Certainly, their production is insignificant, compared to the sex hormones that are released by the testes in males or by the ovaries in premenopausal women. It's a different story postmenopausal, but premenopausal, the adrenal androgens released by the adrenal cortex really is insignificant compared to the estrogen that is released by the ovaries. What is known is that they do contribute to the development of secondary sex characteristics such as hair in the axillary and pubic regions. It's also thought to contribute to sex drive in adult women. And post-menopause, it is a significant source of estrogen in women because, again, a percentage of those androgens are converted to estrogen. The second type of hormone released by the adrenal cortex is aldosterone. And aldosterone is what is referred to as a mineralcorticoid. So you want to add this term to your slide, a mineralcorticoid, and its name implies mineral. It's going to regulate a mineral, and in this case, it regulates potassium and sodium. And as it does that, it influences water balance, and we'll get into that in just a second. Stimulus of release. So there are several stimuli that cause the release of aldosterone. Two are humoral and one is hormonal. First of all, low blood volume or low blood pressure will stimulate the release of aldosterone. High blood potassium will also stimulate the release of aldosterone. And a hormonal stimulus that will stimulate the release of aldosterone is ACTH, adrenal corticotropic hormone. So in addition to causing the release of adrenal androgens, it will also cause release of aldosterone. There's also another chemical called angiotensin II, which is a hormone that is produced when blood pressure falls, that also will stimulate the release of aldosterone. Now, if you think about what causes the release of aldosterone, it will give you an indication as to what aldosterone will do. So aldosterone, once it's secreted into the blood, it targets the kidneys. And what it does is it causes reabsorption of water by the kidneys in order to maintain blood volume and blood pressure. So if the kidneys are going to reabsorb more water, then they're basically going to decrease urine production. So urine will tend to be produced in smaller amounts and it's more concentrated. Aldosterone does this by stimulating the reabsorption of sodium ions from what's filtered from the blood. As sodium ions are reabsorbed, chloride, which is negatively charged, follows. And as sodium and chloride, salt, is reabsorbed by the kidneys, water sort of follows by osmosis. So there's an old adage that says water follows salt. So wherever salt goes, water follows. So if the kidneys reabsorb sodium and chloride, then their water is going to follow, and water is going to be reabsorbed. As sodium ions are reabsorbed, they are exchanged for potassium. So potassium is lost in the urine. I'm going to use this figure here to sort of illustrate in very basic terms how aldosterone enhances the reabsorption of water. So what you're looking at here on the left is a frontal section of the kidney. Here you have in red arteries bringing blood to the kidneys. That blood is flowing into capillaries around nephrons. This is a nephron, what you see here on the right. As blood flows through the capillaries, blood is filtered from those capillaries the filtrate, most of which is then reabsorbed back into the blood, and then 99% of what was filtered was reabsorbed and then returns to the bloodstream. Another 1% that was not reabsorbed is what we call urine, which is basically water with a high concentration of waste products and substances that the body doesn't need. They flow into these calyces here, and then those calyces merge into the ureter, and then the ureter takes the urine down to the bladder where it's stored. If we were to magnify these capillaries and nephrons, we'd see something similar to this here on the right. Here we have arteries bringing blood to the nephron, and here is where the blood is filtered. And basically, just think of everything in the plasma, for the most part, being removed from blood. And that includes things that the body needs as well as things that the body doesn't need. And then as that filtrate, as it's called, moves through the renal tubules, about 99% of what was filtered is going to be returned to the blood. So in other words, it's going to move from the renal tubule back into these capillaries you see here. Now we're going to focus specifically on sodium and water. So as it moves through, sodium, indicated by the green arrows, is reabsorbed. And then as sodium is reabsorbed, chloride is reabsorbed, and then water sort of follows. Aldosterone enhances the reabsorption of sodium and chloride and water from this part of the renal tubule here and this part as well. So aldosterone, in response to low blood pressure, low blood volume, increased potassium, causes reabsorption of sodium and chloride and water. Also, as sodium is reabsorbed, although not shown on here, potassium is secreted into the renal tubule. In AMP2, this will be covered in much greater detail when you cover the urinary system. This brings us to regulation of aldosterone, which of course is by negative feedback. So a drop in blood pressure or high blood potassium causes the release of aldosterone. Aldosterone then targets the kidneys, causing the kidneys to reabsorb more sodium, chloride, and then water follows. So we have an increase in reabsorption of water. I said that sodium is reabsorbed at the expense of potassium, so potassium is excreted. As water is reabsorbed and as calcium is excreted, blood potassium is going to be lowered and blood pressure will rise. Both of those changes will inhibit further release of aldosterone by the adrenal cortex, and it'll also inhibit further release of adrenal corticotropin, which is another stimulus for the release of aldosterone by the adrenal cortex. So again, classic negative feedback. Let's now discuss the last type of hormone that is produced by the adrenal cortex, and this is the glucocorticoid cortisol. Cortisol is a glucocorticoid, and just looking at that class of chemical, you can probably imagine what it's going to do. It's going to have something to do with the regulation of glucose, which it does, which you will see in just a moment. Stimulus for release is ACTH. So adrenal corticotropic hormone targets the adrenal cortex, causes the release of cortisol. Now, normally there are bursts of cortisol secretion that occurs in a regular pattern throughout the day and night. The blood levels typically peak after we rise, and they're lowest in the evenings just before we fall asleep. And these cycles appear to be determined by our normal patterns of eating and activity. These patterns can be changed due to stressors that we encounter, like a major loss of blood, or a pretty significant infection, or physical trauma, or even emotional trauma. The central nervous system can also override the inhibition of adrenal corticotropic hormone and cortisol releasing hormone in times of stress, leading to increased cortisol secretion. Overall, the effect is cortisol helps the body deal with long-term stresses, or stressors, I should say. I want to contrast this with acute or short-term stress. Short-term stresses the body responds to by secreting epinephrine and norepinephrine from the adrenal medulla. This is the fight or flight. That is dealing with a short-term stress where you're having to flee from danger or fight for a very short period of time. When we're talking about long-term stress, it can be situational, where there is something traumatic that's happening in your life. It could be loss of a loved one. It can be a divorce. It can be just something that affects you deeply, emotionally, and mentally, and potentially physically. It could be a major surgery that's going to take weeks for you to recover from. If you were lost in the woods for a number of days with limited access to food or water, that's the type of stress I'm referring to when I refer to long-term stresses. So cortisol helps the body adjust and adapt to long-term stress. Cortisol pretty much targets all cells of the body, and it acts to raise blood glucose levels, particularly during the time when you are in a stressful situation, during a fast, or if you have high energy needs. By maintaining blood sugar levels, it helps you resist these long-term stressors. How does it maintain blood glucose levels, particularly if you're not consuming carbohydrate? Well, it promotes the breakdown of fat and protein to then be used in the synthesis of glucose. And if you recall, that process is called gluconeogenesis. So even if you're not consuming sufficient amounts of carbohydrate, or any carbohydrate, say if you were like lost in the woods for 3 or 4 days, right? Your body would be able to maintain its blood glucose levels by breaking down fat and protein and using it to make glucose. Cortisol also helps maintain blood pressure by causing a generalized constriction of blood vessels, and it is also anti-inflammatory. Now, this may sound a little counterintuitive because you're probably thinking, I need my immune system to be working normally when if I were injured, right? If I had a major surgery. And that is true, but you also don't want your immune system to go too far. You don't want a severe inflammatory response to your surgery or your injury. And so cortisol helps put the brakes on the immune system because if it reacts to too much, it can actually cause damage to the body. Hypersecretion of cortisol, that is, if above normal levels are secreted, it can inhibit inflammation, it can depress the immune system and white blood cell formation. It can also interfere with the skeletal system, and as you would expect, it can cause an elevation in blood sugar levels or hyperglycemia. While we're talking about the anti-inflammatory properties of cortisol, I want to talk a little bit about its effect on the immune system over a long period of time. So you've probably been told that stress can weaken your immune system, and there is something to that. If you are undergoing a very stressful situation for a prolonged period of time and significant amounts of cortisol are being secreted for this prolonged period of time, it can suppress the production of white blood cells. And of course, that makes you more susceptible to infection and colds and other acute illnesses. So there is something to stress causing your immune system to be weaker than it otherwise would be. Before we end, let's review the learning objectives of the screencast. We discussed the tropic hormone ACTH, which is released by the anterior pituitary gland and targets the adrenal cortex. The adrenal cortex, in response, then releases adrenal androgens, aldosterone, and cortisol. Remember that for each hormone, there are a list of features that you need to know. I provided you with a hormones and their properties table, which allows you to summarize all of the information you have to know for each of these hormones.